Okay, well, so let me introduce some new generation of lithography. So, as I said, people start using either deep UV light. There is other way that also available like electrons and X-ray and ions. So, uh, you know, because of that, people try to using the different sources because the pattern sizes depends on the wavelengths of the source. Okay. Um, for example, the start people using the electrons to just direct writing. This is like a direct writing. It's called e-beam lithography. Uh, so instead of using the photomask and then using the copy the pattern of the mask directly into the substrate, basically this is like a scribing the pattern by the e-beam, electron beams, right? So because the e-beam is a has a like a much this is electron beam is a much smaller dimension than comparing the UV or any other the visible photons, right? So that's why you have a higher resolution. That's like resolution of a point line with say like a point 0.1 micron is easily achievable. And then people using also the X-ray for the same reason, and but in that case, you need like a mask necessary to do that, and then in that case, the resolution is zero point 0.2 micron. Or so ion beam also can be used as a direct writing, and then the resolution is zero point 0.1 micrometer. Okay, so well, just this is kind of demonstration for the either is electron beam is available to look at. So there are simple setup also available to generate. At the end at sea, people set up like a generator of E beam, and then they put some object in the middle, and then you see the image of that object and on the screen at P. So that shows like the E beam actually uh, can generate the like a like a pattern, then it's useful to use it. And the other way to for the lithography is called immersion lithography. So uh, the way it works is under the like a liquid condition, right? Under the liquid condition between the wafer and then the lens or writer. Uh, the lithography is done under the liquid condition. So comparing the air condition, liquid condition, I think you have a better environment because another liquid under the water, uh, you have less uh, optical diffraction and then the refraction. So and then also under the water, their refraction index is more advantageous than the air. So there are some advantages that the lithography done in water, so that improve the resolution as well. Okay, so let's talk about the photo mask. Uh, to usually people really don't know about how to generate the photo mask because you design the mask, you design the mask, and then actually you send this design out to the photo mask makers, and then they generate the photo mask for you. So people usually don't know how they're making it, but usually they pattern the photo mask on the glass substrate, right? It should be transparent, and then the mask pattern usually patterned by the chrome. So um, so a type of the general photo mask is a chrome on soda lime glass. That's the most common type of the photo mask. Okay, and then well, depending on the photo mask makers, right? Either it could be patterned by e-beam lithography or pattern generator. It's just the general way like a lithography. Okay, um, and then or you can make chrome on coarse glass, and you can use the other, rather than the chrome, you can use other materials as well. Um, so for the high resolution, you need some, the laser printing is also available. Well, the size of a mask, basically 4 by 4 inch mask is good for 3 inch wafer. So wafer is circular, right? You know, but the mask is rectangular because the mask holder, they need a kind of a hold, firmly hold the mask, so it's rectangular, right? So mask size should be larger than the wafer size. So that's why the mask size is larger than the wafer size, like a 5 times 5 inches used for 4-inch wafers. Well, so as like a negative photoresist, positive photoresist, you can have choice whether the dark field or the light field. So you have choice that it depends on the photoresist as well, right? When you design the mask, right, the light field is the means uh, you have a you have some, if you draw the pattern, right, the pattern will be uh, protected, right? If you draw the pattern will be protected, right? So usually the shape of the mask is called, it looks clear because your pattern is usually less than the empty area. Okay, the other side is dark field, right? So your writing pattern becomes clear, right? So this is combination with the photoresist, either negative photoresist. You should decide either way of a polarity. Um, that's the you should choose when you order the mask, photo mask to the vendor. They are asking whether it's dark field or light field, so you should determine those two polarity. Okay, so right, uh, so how to make the photo mask? So you usually design your pattern in like in CAD, like AutoCAD. Any general CAD is okay, and then like mask and wafer device size you should determine, and then you should determine the layers, like how many masks you need to put certain pattern, right? So for example, if you wanna your like a MEMS device, it's like this. It's like looks like this cantilever. You see this so cantilever shown here, right? This is like a side view of this. Then basically it used the part of silicon as your cantilever beam, silicon wafer. Okay, and then I see like a bottom, certain part of the pattern was deposited, and then the volume was deposited, the boron was deposited. Okay, and then that means this silicon is semiconductor, right? So I believe this is not conductive, right? And then you make boron diffusion a certain layer. So this is boron diffused area is conductive, silicon uh, silicon layer, and then you put in dielectric material like silicon dioxide, and then you pattern these two areas to make some hole, and then you have a connection with the metal layer like aluminum. That's what like build up, and then to make this cantilever structure, actually you have a back etching done, so you have some space underneath of cantilever. So that's kind of the MEMS device you may want to have it. Then the question is like, how many masks do you need to make this pattern, right? Uh, that's the that's you determine like that's why you need a multiple layer, right? You may need one mask to this backside etching, right? You may need another mask like to make boron uh, diffused areas, so on, so on. So just think about it. This will be eventually will be your homework. So okay, all right. So and then the photolithography process, like it could be done very clean environment, right? Also the it should be block any this is only is right because your photoresist is sensitive to the light, right? You should protect this your photoresist. So your cleaner environment in this photolithography station, uh, you should allow only the light that doesn't affect your deposited photoresist. Okay. So the cleaner facility should be very very fine. Okay. So usually people using like a class either 1 or class 10 for the photolithography process. Okay. So class 1 means like you have only one particle per cubic foot. Okay. So its number is become small, right? We just use 1 or 10 or 100 or 1,000, but if you're getting the like a number is getting larger, it's getting 30, right? So it's usually people say that if you want to remove the one digit down, right? One digit down, then you should spend like a uh, uh, 1 million or 10 million. That's kind of the range that you should put into the money to to make that clean room is that clean. Okay, in that the photoresist station actually you should be done the vapor cleaning, right? Even though you receive the vapor directly from the like a vendor of the vapor vendor, some you may need a surface cleaning first, okay, and then you put the photoresist on top of it, and then you coat uh, by spinning, and then uh, you should like to spin the photoresist should be soft baked, like you bake at certain temperature to remove solvent. Okay, solvent is not helpful during the exposure. So you need solvent to spread out the photoresist. So its role is done. So you don't need solvent anymore. So during the pre-bake you remove the solvent, and then sometimes you need alignment between the mask and then the vapor, and then after alignment is done, okay, and then you can expose the UV light, okay, and then after the UV light exposed, and sometimes depending on your photoresist, either you have a post exposure bake is necessary, or sometimes you don't necessarily have that step. So usually a photoresist company provides certain information that you should do any particular procedure. Okay. Also, they provide like spinning speed versus the film thickness table or plot, so you have certain idea depending on the like RPM, how thick your photoresist will be based on their like spec sheet. Okay. After exposure or some after post exposure bake, and then you need to put this vapor into the developer, right? This developer, depending on your photoresist type, can remove either exposed area or it can remove unexposed area, right? So, and the developer is over, then because you're gonna use this pattern uh, for the subsequent procedure like etching or deposit, right? You wanna make securely uh, hold those photo developed patterned photoresist. To do that, actually you need to do post bake. So this is like called hard bake. So basically, you kind of a little higher temperature than the post soft bake. You kind of remove out any rest of the solvent, and those things to just make stable structure. That's the making the last step of the lithography. Well, if you need to like repeat for the same procedure with the same vapor, then you should strip the patterned photoresist. So that's called stripping. Okay, so sometimes you need just solvent is necessary to remove, but sometimes you have a certain stripping machine is available also. So, or if your stripping is not working, there is called post-processing cleaning as well. We call it etching. That's kind of plasma cleaning. So you can completely remove the remained photoresist using this etching procedure. So this is general photolithography procedure. For wafer cleaning, um, you have a, usually the wafer have a typical contaminant, like from the atmosphere. If there is dust, bacteria, or sometimes a fingerprint. Uh, and then during the photolithography, there is photoresist residue, or if you want to recycle it, and then solvent residue. Uh, okay, and then there are some water residue. So you want to remove those contaminants before use the vapor for photolithography. Okay, so for organic cleaning, right? So usually you put the soak in TCI is kind of solvent or as acetone. Okay, and then you put the methanol again, and then the put cleaning in DI water, and then you kind of dry the vapor with the nitrogen gone. So that's kind of a standard way to cleaning. Or sometimes you can use these two combination of the cleaning liquid. We call this piranha cleaning to remove your contaminant. Or sometimes you have RCA cleaning is available. So there are some batches of the uh, cleaning liquid is available. So usually the cleaning has this cleaning batch is available. So you can go and then put this vapor into this environment, and for certain limited time, then you can remove it. Okay, and then make sure you have dehydration bake. So make sure your vapor is dry condition. Okay, so there is some dehydration steps to be done after this cleaning, like put them in in vacuum. No, it's a convection oven, and then make sure they are kind of cool down before they expose of lithography and you know, the other procedure starting before the starting of the procedure, because the hot vapor, they have different temperature, different properties at and high temperature, and then they eventually, if they are cooled down, their volume also is a little bit is reduced, right? So those changes, you do not want to see that happen during your process. So make sure you have dehydrate the vapor, and then make sure it's cooled down to the room temperature, and then they are ready to use again. Okay, spin coating. So these are the like a shape of the spin coater. There is like a chuck that then can hold the vapor with the photoresist on that will be deposited on top of the vapor, and then between the vapor and then this vacuum chuck, there is vacuum will be applied after a little alignment is done, and then you spin the vapor, and then you deposit during the spinning of the vapor that you depending dispensing the resistor. Uh, so again, those photoresist vendors, they provide the spinning speed versus film thickness um, data, like a chart. So, for example, depending on SU8 uh, product, like let's say you choose the SU8 uh, uh, 2100, right? This is like this sky blue plot here. Then if you wanna like a thickness of like 200 200 micron, then your RPM speed should be around 1500 RPM, right? So in that way you can use this chart to kind of figure it out your spinning speed. Okay. Um, So, well, there are some equation is available depending on like viscosity, so on. But I'm not going to go over in detail. But this plot is really good to determine your spinning speed. So primer is sometimes used to enhance the adhesion between the photoresist and the substrate. If you really want to have good adhesion, you can apply the primer first and then you can apply the photoresist after that. So that's primer actually enhance the adhesion of the PR to the substrate. It also is very thin, so you don't need to worry about its effect to the thickness on the patterned photoresist. Okay, so soft bake, again, the pre-bake, this is the procedure that you want to remove the solvent, right? So after spin coated, the resist still contain up to 15% of solvent, and it may contain the built-in stresses. So again, so you want to contain only one material. If you multiple material, and then eventually then cause the stresses in structure. So because its role of the solvent is over, you want to remove the solvent. Okay. So vapor is baked to remove solvent and stress and also to promote adhesion of the resist layer to the vapor. So the general way for the soft bake, you put either on hot plate or on even on oven. So in hot plate, you need usually 80 to 90 degrees C for 1 minute. The convection oven, you need a little higher temperature, 90 to 100 degrees C for a longer time, like 20 minutes. Because over here, because heat conduction through directly from the hot metal plate to the substrate, their temperature rise up quickly, right? So that's why you need only 1 minute to do that. And by the way, in convection oven, because heat was delivered through the convection in the air, so your vapor is eventually rising the temperature slowly, and then it takes time. Okay, so I really strongly recommend to use the hot plating uh, soft baking because it saves your time. Okay, so that's why I'm talking about these two lines on there. So alignment exposure, this is one of the machine that used in one of the clean room actually at Georgia Tech. At the time, I was in the clean room in 2002, so that's kind of the age that's shown over here. So there is MA6 mask aligner, and then there is another aligner is available. So over here you see this is like a vapor holder here, and then this is for you can exchange it, but this is for like a 4-inch vapor holder. So they can apply the vacuum, then they hold the vapor, and then over here is this is called the mask holder. So you can take it out and then put in your mask and then put it back, and you can apply the vacuum to secure the location of the mask. And then if you decide their contact mode, and then if you put the contact, and then this mask holder will be getting closer to the vapor holder, and then through the microscope on top of the uh, uh, mask or underneath of the camera, through the screen you can can do some alignment between the pattern on the vapor or a pattern on the pattern on the mask. And then if the alignment is over, then basically you expose your UV light lamp, UV light through the lamp, and then you set certain time of the exposure and then intensity as well, and then just expose, and then that's it. Uh, basically, okay. Okay, so some alignment step over there. Usually we use like a cross mark to align between the mask and then the counterpart of the pattern on the vapor. So from the top view, and then you can use mask you can use the microscope object lens to look at this alignment pattern carefully. Sometimes you need to look into the uh, backside pattern, because if you want to do backside wet etching, you need a pattern the other side of the wafer. To do that, you should do, but still you need a good alignment, right? So from the backside, in that particular mask aligner, they provide a camera. This camera actually take a look into the microscope object, and then you provide the image to the uh, microscopic view, and then you can do like a backside alignment through the backside of microscope object. So that's very interesting, right? Okay, so that's what possible for backside alignment. All right, let's stop here, and then we'll continue the lecture.